Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 27, we will talk about the foundational theories which we should be aware of when we are talking about machine learning. So, the different concepts that we will cover will be the foundational theory, what's its requirement before we learn machine learning. Then we will get into deeper into linear algebra, probability and statistics, optimization theory, information theory, learning theory, graph theory, and ethics and fairness in machine learning, and finally we will end with algorithms and data structures. Now, machine learning, as we have learned in our previous lecture, is basically where we have a loss function, that is a sort of a equation that we are trying to fit in a data. But there may be other kinds of programs as well. But fundamentally, it is built on mathematics, statistics, optimization, and this kind of aspects, this kind of theories. So before we go into machine learning, we need to understand what is involved, right? What are the things you need to study? Now, it doesn't mean that you need to know all these aspects in detail. Along the way, as we go along, learn about certain models or how it is applied in our context, then we will also learn the details about it, right? So, in this particular lecture, we are just summarizing the broad theories or the broad fields which are connected with machine learning. Sometimes machine learning models are referred to as black box models. That means some people say that, well, machine learning models, we feed the data, it will give you a prediction. It's not true. That means it is like if the models, if we know that what mathematical theory has been utilized or what is at the back end of it, we will be able to interpret the model, right? There we will be able to interpret, we understand the structure, how the decision has been arrived at, and also we will understand the principles behind that, right? So that means it will help us to say that, well, because of this is the prediction. That means it is not out of the blue something is coming. So these theories, of course, that means based on the kind of data that we are using, what output we want, and the assumptions and the theories that we apply, and then that means this will guide the choice of which machine learning model we are going to utilize, and then how to interpret the results of that particular model. So specifically, there are many aspects which needs to be studied when we are learning machine learning, but you will see that mostly we will be touching upon linear algebra, probability statistics, optimization theory, information theory, learning theory, graph theory, and these are the different things that we have to do. Then ethics and fairness is, of course, certain aspects which we have to be aware of when we are building machine learning models. And the algorithms and data structures, again, it's coming from the computer science domain, but it is mostly for sorting data, searching data, organizing data, those kind of aspects, and how to do it faster and all, because we are dealing with data, and if you don't know how to get the results out practically in a efficient, fast way, then we may not be able to develop very good machine learning models. So that's why algorithms and data structure is also important. Now let us take one example, information theory, right? When we develop decision trees, we utilize this particular theory. The concept says that more is the entropy, or rather the quality of the decision is less in this particular case, right? So that concept comes from information theory. So when we will learn random forest or decision tree or some other kinds of ensemble techniques of decision related with decision trees, we will learn the information theory to a certain extent as per required to develop that model. But at this point, we are trying to understand what are the broad group of theories which influence, or rather based on which machine learning models are developed. One thing we need to understand is, in machine learning models, data is the key. That means most or all machine learning models operate on numerical data, or rather numerical representations of the data. That means even if I take an image, I am trying to analyze, is it a cat or a dog, I have to convert that image data from that particular format to something of a numerical format, right? Then only a machine learning model can analyze that result data and then come out with predictions. Okay. So this data could come from surveys, sensors, satellite images, or could be some sort of some text or document. Anything could be possible. So the first group of or rather the first set of theories that we need to understand is the theory of linear algebra. That means in most cases, any single observation in machine learning, as I was telling that we have to work with data, numerical data, it is treated as a vector, right? And this vector is in a multi-dimensional space, right? So that means in machine learning, every observation based on many features, many aspects, we get a certain kind of result, right? So, or sometimes there is no result, only the vectors are there, right? And we need to make sense of what is what. So, where each dimension corresponds to a feature. For example, I am predicting, for example, PM 2.5, one of the vectors is of course the traffic count in that particular road, for which I am trying to estimate PM 2.5. It could be like the time of the day, that could be another feature, right? Another dimension. So, these are the different features, and the data is actually covering, it's a vector data in a multi-dimensional space. So that's why linear algebra is important to analyze this sort of data. So most of this data is organized in form of matrices, right? So machine learning algorithms operate on these matrices. So all the different aspects how matrix computation happens, it is part of linear algebra, and that we have to understand. So the data set is the matrix. Rows becomes observations, rows are observations, columns are the features, and everything is stored, matrix operations are conducted to come out with the solutions. And this enables, when we are converting these tables into matrices and we are computing on that, it increases the efficiency quite a bit. And then there are many machine learning techniques which requires transformation of the data, like scaling or rotation of the data. That means scaling means normalization or those kind of scalings, right? And rotation of the data means that means we are transforming the orientation of the data so that we can more clearly we can see the patterns and so on. So in principal component analysis, we more or less do this kind of transformations. So that means it could be feature transformation into new space where patterns becomes clearer and easier to model. So this kind of mathematical techniques also is part of linear algebra. Then variance shows, if I take the variance of the data set, how much the data is spread out, and that help us to identify many things, and it will tell us that okay, in which the spread is usually in which direction it is more, and it can help us in even reducing the dimensions, or it could tell us that okay, these are the extreme values, those could be removed. So all these things could be looked into. So usually we are focusing on vectors, matrices, matrix manipulation, eigenvalues, eigenvectors, singular value decomposition, singular value decomposition. So these are the different things we will come across during our machine learning, learning of machine learning models or tools or methods. So linear algebra forms the backbone of many machine learning algorithms and is central for principal component analysis, support vector machines, neural networks, and so on. The next most important thing is of course probability and statistics. Without that, many of the models which we are developing in machine learning cannot be developed. And not only that, in most of the models there is some application of probability or statistics in some form or other. So in most cases urban data is uncertain, a lot of sensor errors are there is differences in human behavior, so there is random behavior, and then there is probability associated with the behavior, then there is different forms of variability, say for environmental variability in environmental measurements and so on. So that means there is a lot of all this has to be established or computed or estimated. So this probability and statistics help us to measure these different things like noises in data, then incomplete information, random variation, all this could be measured. Then machine learning models usually treat inputs and output as random variables drawn from some underlying distribution of data. That means there is a data set which follows a particular distribution, and we are drawing data from that, right, for any kind of analysis. So this is a basic general assumption which requires us to understand the concepts of probability and statistics. Then correlations, which is like, testing how two variables are related, or it could be how multiple variables are related. And then the causation, that is the actual model, that is I am predicting that this feature is resulting in this certain outcome, right, or this change in the values of these features will result in a change in the outcomes value. So this causation, or what causes what, that's the machine learning model part, right. So correlation, which is a precursor to machine learning model development, this also is part of probability, and we use the fundamental knowledge from probability and statistics to do those evaluations. So many ML models estimate parameters by maximizing the likelihood of observing the given data. So that is again statistics. And so again you will see this kind of terms being utilized: probability distribution, it could be Gaussian, Bernoulli, linear, and so on. And then you will come across Bayes' theorem, likelihood functions, hypothesis testing, estimation, sampling methods, expectation maximization. So already some of this we have already come across, right? But you will, in the subsequent lectures, you will when we will get into certain kinds of machine learning methods which requires this kind of fundamentals, then we will discuss those as well. So ML is built on statistical principles. Understanding the role of uncertainty, distributions, data variability is very is common for almost all machine learning models, and it is used for drawing inferences from the data. And for that, suppose sometimes we use Bayesian inference and Gaussian naive Bayes classifiers. Then we use confidence intervals, right? We for understanding the uncertainty in prediction. Then model evaluation and performance, like the bias variance trade-off, cross validation, all these things we could do using machine learning, probability and statistics. Then there is also need to understand the optimization theory, particularly for the learning process, when there is a function, linear, nonlinear, whatever the function is, and we are trying to improve the attributes of the function so that it more matches the data and all. So of course there is to be some form of learning, that is we are learning the right value of beta values, right. So that learning happens via optimization. That means when we are training a model, it means like we are finding the best possible parameter values which fit that particular for this particular context, and so that the prediction errors are minimized. And this can only happen when we adjust the regression coefficients and to overall minimize the difference between the predicted and observed this values of in this particular case predicted and observed values of pollution and traffic flow. So all this, when we are trying to do that, then there has to be a way to keep on decreasing. So that is where optimization comes in. So the loss function defines how model performance can be measured, like for example the mean squared error for pollution prediction, cross entropy for land use classification. So this so we have a regression equation, and how do I measure that? How good is that regression equation? So for that we are using a loss function. So gradient descent gradually updates parameters in the direction that reduces error. So that is where I was earlier mentioning the term gradient in the previous lecture. That basically means that at what rate I will change those parameters which will result in reaching that minimum value of that loss, achieving that minimum or the maximum value of that loss function. So that could be determined. So this gradient descent actually helps in determining that. Then also for understanding this minimum cost function or this loss function in regression models or so on, we have to or understanding like there is a term called back propagation in neural network analysis. That means how the results of how the result could be changed by changing the parameters in and we go from from the results towards the feature, that means towards the values of those features, right? So in a back propagation mechanism. So we will discuss that in detail later. So this is where calculus is also required, right? So our understanding of calculus also becomes important. So we can use take derivatives of a particular equation to arrive at, where dy dx value is equal to 0 to find the maximum slope or so on, and this will help us to minimize the loss functions or to determine the gradients and so on. So within the domain of optimization theory, you will come across terms like convex optimization, gradient descent, stochastic gradient descent, Lagrange multipliers. These are all terms which we can utilize while developing machine learning models, and we will learn those as and when required. So machine learning algorithms typically involve optimizing a cost function to improve the model's predictions. Understanding optimization theory helps in selecting the appropriate method for model training. Now coming to information theory, it provides a framework for understanding the amount of information gained by a particular prediction. And now usually we see it in many cases, but mostly we see it for decision trees and all. So what happens is, when in decision tree, it happens by a if and else rule. That means if I choose something, then it's a if, then there is a result, right? And the result should have, less, that means we should gain some information, or rather this gaining of information, that is basically depends on the amount of entropy. That means if I categorize using a certain variable, and we are saying that, well, this results in less amount of entropy or less amount of variability in the results, then obviously this is a good feature which we can use for prediction. And this amount of information gain that is happening because of utilizing this particular feature for doing the prediction, or in a regression model, if I include a feature, it will improve my prediction efficiency. Then basically this we can say to be information gained, and this is crucial for selecting which features to be chosen in and kept in the model, and for also evaluating the model performance. So in case of decision trees, we measure the entropy. So we measure the uncertainty of a prediction via entropy. That is how mixed or uncertain the predicted outcomes are. That is by low entropy, one means is the outcome is more likely. High entropy means multiple outcomes are similarly likely. That means I am trying to predict, like for example, PM values would be high or low, some category, right? Now I am saying that I am asking a question like, is traffic high or low? If traffic is high, the values would be high. Now if I find, after asking the question, the results I am getting, it is resulting in, that means I am saying traffic level above 500 or below 500. These are the two categories. When it is above 500, or what is happening is, I can say that the values would be, we can say that in most cases the prediction of pollution would be high. Only in few cases there would be low pollution prediction. Whereas if I, instead of using traffic, I use something else, like for example land use, I may end up predicting that, okay, there would be when I'm saying that, okay, these are the what would be the resulting high or low, you will see the results is very mixed. Some will be high, some will be low, right, when the land use is of a certain kind. So that means the entropy is lower, right? So this concept is utilized in the information theory. So quantifying the distance between the probability functions, that is KL divergence, that is how far the models predicted and probabilities are from the true probabilities. So that also could be measured. This is part of information theory, and KL divergence measures how much information is lost when a predicted distribution is used instead of a true distribution. Then there is cross entropy as well, which compares two classes with the probabilities predicted by the model, and cross entropy is basically true entropy plus KL divergence, and minimized cross entropy effectively minimizes the KL divergence. So this KL divergence, cross entropy, all these things are part of this, the basic concepts that we will come to learn when we will learn models which utilize this kind of aspects. So again, the terms that we will again and again learn in this particular kinds of methods are entropy, mutual information, Kullback-Leibler divergence, cross entropy, and so on. So this measures and quantify uncertainty and mismatch between predicted and true probability distributions, and this enables the models to run more accurate probabilistic predictions. Then comes the learning theory, where we have already talked about this bias and variance trade-off. And bias occurs when a model is very simple. That means we use very few parameters or features to predict something. And so that means we have to do very strong assumptions, and sometimes important relationships may be ignored. So that results in incomplete understanding of the patterns in the data, right? So that is bias. And variance occurs when a model is too complex and learns noise instead of true pattern. That means when there is overfitting. That means I put in a lot of parameters, not all of them are contributing a lot, some are contributing less and all. So in this case, the model fits nicely because this is the distribution, the way the data is organized, that actually fits into this particular equation. But because it's a higher order model and I'm taking that model to some other data set, it may not fit, right? Because the variability, a lot of things may be different in that data set. So this is this overfitting. So the idea is we have to choose a rich set of features to do prediction, but at the same point of time it cannot be too much, right? So that means we have to choose the right features for each model. So if it is not done, then it will fit the data. It will fit the model will fit the training data very well, but performs poorly on new data, and will be also sensitive to very small data changes. It will create very different results. So the concept of generalization also, you should understand that good models are complex enough, but at the same time they can capture the real patterns, or they can do the proper predictions. But at the same point of time, these are simple enough. That means it is not like hundreds of features, few features which we can utilize, and we can apply that model in another context, another set of data, so that we can generalize the result we can apply this in the new data, and that means we are generalizing. It's a generalized model which could be applied in any data. So again, the terms you will learn in this particular aspects will be bias variance trade-off, overfitting, underfitting, generalization, empirical risk minimization, VC dimension, probability approximation, approximately correct learning. All these different aspects you will learn. So machine learning theory helps in understanding the fundamental limits of learning algorithms, how to evaluate and improve the generalization performance of models. That has to be a part of this learning theory. That is part of the learning theory, and it is part of learning how to build machine learning models. Then there is also the graph theory. In today's context, we are having very complex set of data connected in a very complex way. So particularly a lot of analysis requires this kind of analysis, where graph, we have to understand the nature of graphs or the graph theory. So nodes, edges, directed and undirected graphs, that is where the movement within that particular network is in one single direction or in both direction. Then graph traversal algorithms. Now that means how do we search inside a graph? That is breadth first search, BFS, or depth first search, and then the shortest path algorithms. All these things are part of this graph theory that we have to learn. So even though it's not one of the basic foundational theories in that strict sense, but in many of the machine learning models in today's context are increasingly using this graph theory to come out with meaningful outcomes. And particularly in the case of network analysis, such as social network analysis, some sort of recommendation systems, deep learning. So this is where we are seeing again and again the increasing use of graph theory. And like in case of deep learning, we use graph neural networks as well, and this is where graph theory also becomes very important for us to understand. So it provides a framework to represent relationship among data points in unsupervised learning, like spectral clustering, and forms the basis of graph-based models such as Markov random fields and graph neural networks. Now again, after that we come to something called ethics and fairness in machine learning. Now this is not like we are every day we are seeing machine learning models are coming and it is being increasingly used in doing automating several predictions or doing certain aspects. So we have to be careful that there is ethics and fairness in its application, right? So that means all the different ethical and social implications has been considered when we are applying machine learning models. So it should be avoided. That means it should avoid reinforcing societal biases or making unfair decisions. So we should make sure that the model is fair, equally applicable to everybody, right? Because machine learning models are trained on data. If you are not having data on certain kinds of population or individual, the predictions could be erroneous, right? So this is where we have to be careful about how do I build the models and so on. So and the models that we build, those has to be that would be used for making decisions, and those has to be also interpretable to a certain extent so that I understand what is happening. So that is where that means this within ethics and fairness domain, we will talk about bias in data, fairness, transparency, interpretability, accountability, all these different aspects which is more like what model. It's not like just building a model, but is the model really appropriate? Does it serve everybody? Does it serve the purpose why I'm building it? All these questions needs to be answered. Finally, coming to algorithms and data structure, as I told earlier, that means it involves sorting, searching, dynamic programming, developing trees, graphs, hash tables, and so on. So that's why it is crucial in understanding, in designing machine learning systems, and particularly in very large data sets, we have to search for data, find the data. So it becomes part of the machine learning programs that we develop. And so particularly in high performance computing, definitely this becomes even important. So all this storage of data, retrieval of data, all this involves this sort of the algorithms and data structure actually helps in dealing with all these different aspects, and that's why this is also part of understanding the basic foundational theories of machine learning. So these are some of the references that you can utilize. And to conclude, foundational theories explain how machine learning models learn from data, manage uncertainty, generalize beyond samples, and support reasonably responsible urban decision making. Thank you.